All right, everybody, welcome back. So for today's course, we're going to have, last time we actually talked about the linear regression with Spark, right? So we saw some code examples of how you could implement linear regression in Spark. And we didn't actually finish the discussion, especially about the transformers and estimators. So we're going to continue to work on that for the first half for today. And then we're going to move on to the new topic of distance functions and similarity search. So I've prepared a base code for you to kind of jumpstart for today's session. You can find it on Icon. Just click on the base code for October 15th. Okay. And then if you click that, then you're going to see this. Oops. I'm sorry. Just 1 second. Okay, there we go. So if you click that code, then you're going to see this 2020 October 15 base code. And it contains all the routines and everything for, setting up PySpark and downloading the data set. So please go ahead and run all the cells. In your case, I think you will need to create a copy of your own version. So I'm going to actually do the same thing. So I'm going to just create a copy and go from there. So again, this is a base code. So I don't think I need to explain what this is. We've seen this quite a while. So this is a code for configuring Apache Spark and Collab environment. We're going to create a new session called a wine quality because that's the name of the data set that we'll be working on. And then last time we downloaded the red wine data set and the white wine data set. And then we combine those separate CSV files using the union command, right? And before to do that, we added another column called type, okay? And then for red wine tables, we fill that column with this, this new literal red. And then for the white wine table, we have filled that column in with this, string variable white, right? So here's the code for that. Now, one thing that we were working on last time was this this notion of transformers and estimators. So since this is an important concept, let me try to emphasize that one more time. So in Spark, there are two big pillars that defines the development philosophy of Spark. One is a transformer and the other is an estimator. So an estimator, the job of an estimator is to take in a data frame as an input and then produce a transformer, right? And then the transformer is an object that converts one data frame into another, okay? So in case of estimator, the reason why its name is an estimator is because from a data frame, you're inferring some, you're deriving some, internal parameter. You're estimating some internal parameter from a data frame, and that's where the name came from. So it kind of abstracts the idea of training a machine learning model. Remember, if you have a machine learning model, what happens here is, inside of the machine learning model, you have some model parameters. In case of linear regression problem, for example, the slope and the intercept, those two are the internal parameters. And what you do is to take in a data table, and then based on the values in the data table, you tune and estimate the parameters inside of the linear regression model. So, it kind of generalizes and abstracts the concept of machine learning model using estimator. And then transformer is literally you transform one table into another. So, those two are the most important concepts. And then as an example, we saw this object called the string indexer. So string indexer is one of the estimators that exist in this PySpark.ml.features module. And what it does is here in the data table, let me try to show you more explicitly. Let's say let's draw print out three rows. So the column that we added at the end has a string type variable, right? It's either red or white. So in order for us to put this into a machine learning algorithm, you probably want to convert this string variable into a numerical variable. So remember, that's why we used the string indexer last time to convert this type column into a numerical index. And the reason why this is an estimator is because by taking in a data frame, it first of all counts how many unique strings are there in that particular column. right? And then the transformation process has to be dependent on how many columns are, how many, unique string variables are there. So in our case, we have only two, red and white, but you can easily imagine a situation where you have a lot more string variables, right? Let's say you're talking about a chest X-ray data set, then you can imagine a column where there's a disease type annotated. In that case, you're going to have more than just two classes, right? In which case you will need to first of all count, how many unique entities are, included in that column. And then based on that, you have to develop a logic to convert, okay, pneumonia is going to be index 0, pneumothorax is going to be index 2, and so on and so forth. So that's why string indexer is an estimator, and that's what we discussed last time. And the estimators in Spark, they come with this function called fit. Okay, so one way to differentiate or distinguish, estimators and transformers is by looking at the member functions. If it comes with the fit function, then it's an estimator. If it comes with a transform function, then it's a transformer. So with the string indexer, what we first do is to estimate by using a data frame the transformer object, okay, as a result of that. And then the transformer object is now ready to transform a data frame and then convert that into an indexed data frame. So that's what we covered last time, and that's where we stop, okay? So as a result of that, maybe I should run this first. So if you run this code, then as a result of that, what we get is a new data frame that contains a new column called the type ID. Type ID is the output of that transformer that we created, right? So type ID column has been created, and then numerical indices are assigned to each of the rows. So you can see that the red wines now have a numerical index of 1.0, and then here for white wines, so that's got to be df indexed type equals to white. Indexed. Then as you can see over here, the type ID is 0. Okay, so we just assigned a numerical index to each of the rows depending on the type of wine. Okay, so yeah, of course we could have created our data frame instead of putting a string variable red and white. We could have just began with 1 and 0, but that's probably too simple, and we're simulating the real world situation where the data, by default is given in string variables. So in that case, understanding, what string indexer can do can be quite useful. So nonetheless, the main takeaway message again is the syntax of estimator and transformer. So, down the road for the rest of the semester, we're gonna see a lot of different machine learning modules that's available in Spark. But at the end of the day, those are all just a collection of estimators and transformers in some sense. So once you get used to the notion of estimators and transformers and their syntax, then picking up some other machine learning modules is not going to be difficult at all. Okay, so in some sense, what we're doing right now is probably the most important lab section out of all lab section that I prepared for this entire semester. Okay. Now, with that said, okay, there is still, another problem. Well, in case of this data set, it should probably be fine. But, another useful thing is to be able to convert this into what is called one hot encoding, or a dummy variable representation. So for those of you who already forgot, or never heard of what those things are, imagine you have a problem of, you have a column where the elements are comprised of dog, cat, and I don't know, what's your favorite animal? Dolphin. Yeah, there we go. So we have 3 classes now. And the string indexer basically maps them into some numerical values, right? So dog becomes 0, cat becomes 1, dolphin becomes 2, and that's what string indexers do. But in some situations like this, the numerical indices might be misleading, because numerical indices, since they are integer numbers, they have magnitude, right? 2 is bigger than 0, 1 is bigger than 0, 1 is smaller than 2. So we start to have a notion of index versus the original source of data, dog, cat, dolphin. I mean, they don't really have any magnitude. You cannot say, cat is bigger than dog, or, dolphin is lesser than cat. I mean, that doesn't make sense at all, right? So that's one problem of converting a categorical variable into a numerical index. You are falsely introducing a notion of magnitude. So a better representation is, in fact, to map this into what is called a one-hot encoding or a dummy variable representation. So the way to do that is basically, map, for example, dog into a vector, a binary vector, 0, 0. Cat becomes, well, let me take a step back. Let's make a three-dimensional one. And cat becomes 0, 1, 0. And then dolphin becomes 0, 0, 1. Okay. So, you can think of each of the elements in this feature vector as kind of a switch. So if you turn on the first switch, that it means that particular data sample is a dog. If you turn on the second switch, that means it corresponds to a cat. If you turn on the third switch, it becomes a dolphin. Okay, so this is what is called a one-hot encoding, or sometimes it's called dummy variable representation. Okay. One step further from this, what's even better is, if you think about it, it is kind of, redundant, right? You can actually make it more succinct by eliminating one digit. So you can actually just get rid of the first element at all, like this. Then the representation becomes, well, if you have just all 0, then it's a dog. If you have the first switch on, then it's a cat. If you have a second switch on, it's a dolphin. Okay. And, there's no problem indicating the class of the data sample, right, using only 2 digits. So when you have n classes, then you can have a one-hot encoding with an n-1 variables, n-1 elements, n-1 dimension. Okay. So that is what is called a one-hot encoding. And obviously there's no notion of magnitude in this case, right? Those elements, those positions are simply just a switch, right? Indicating the category of the things. So this is actually a better representation for things like dog, cat, dolphin, okay? Of course, there are exceptions. So don't just, take this as is. So let's say you have, class labels like low, medium, high, okay? Then, the string indexer is going to convert that into 0, 1, 2. And, in many cases, this representation is perfectly fine, because low, mid, high is a concept that can be compared, right? High is literally higher than mid. Low is literally lower than mid or lower than high. So assigning numbers actually kind of makes sense. So in that case, you don't probably want to bother to convert them further into one-hot encoding, okay? So I'm not saying whenever you see a string variable, you have to convert that into one-hot encoding. You have to make your own decision in the context of the data set, in the context of what that specific column represents. So anyways, going back. So what we're going to do is to convert the numerical IDs into one-hot encoding. And spoiler alert, if you just look at the result of that, it's going to be actually the same, because we have red and white, right? And then the numerical indexing of that is 0. Well, actually, white is 0. So let me switch the order. So white wine has a numerical index of 1. Red wine has a numerical index. Sorry, white wine has a numerical index of 0. Red wine has a numerical index of 1. And if you convert that into a one-hot encoding, then white wine will become 1, 0. And then the red wines are going to become 0, 1. And then by convention, we decided not to use the first element. As a result, at the end of the day, it becomes exactly the same as the numerical indices. So in this case, I mean, this is a binary classification problem, or binary, type value. It's either red or white. So in this case, there's no issue. But let's assume that there's rosé. and in that case, you're going to need another index. And from that point, you start to have a problem. So we're just assuming a generic situation like that. And then we'll try to convert this numerical indices into one hot encoding. Okay. So for that, again, the go-to place most of the time, if you're looking for some predefined estimators and transformers to convert one representation to the other, always the go-to place is pyspark.ml.features, feature. And then you can import from that module. And if you look at the the drop down, the autocomplete suggestions down there, you'll see one hot encoder estimator. Okay, so this is the one that you're looking for. So one hot encoder estimator, like the name indicates, it's an estimator, obviously. What it does is it goes through a column that contains the numerical indices, and then it counts how many how many unique numbers are there, how many unique indices are there, and then it creates a vector of n-1 dimension, and then it prepares to convert from one numerical index to the other, to one hot encoding. So the encoder is defined as one hot encoder estimator, and then similar usage. So here for string indexer, the arguments to that string indexer object was input column and output column. So one hot encoder is pretty much the same, except that input calls, there's plural, and you can either just select one column, or you can go with more than one column. So for some reason, one hot encoder estimator is, I guess, a little more versatile, right? Because you can have more than one column specified as input, and then same thing with the output. So, but anyways, that's pretty much the similar syntax, similar usage. Now, like I said, encoder is an estimator, so there's got to be a function called fit, right? And what you do is to convert the indexed data frame, df_indexed, into something else, right? So here, I'm gonna, what was my naming convention previously? Yeah, just encoder_transformer. So that's gonna be my transformer, okay? So again, this is an estimator. So by digesting a data frame, it returns a transformer that transforms, that is ready to transform a data frame into something else. So, the final thing is pretty straightforward. So df_encoded, that's a new data frame that we're going to create. And that's going to be created by encoder transformer. And it'll transform df indexed. Okay. And df encoded dot show. Let's display only 2 rows. So as a result of learning this, now we have a new column called type1 hot added. Okay. But wait a second, if you look at this, it looks kind of weird, because I promised you that after one hot encoding, you're going to see a vector that looks like either of these, right? But it seems like we have some weird thing in the table. What the heck is that, right? So in fact, Spark actually uses a pretty clever representation, what is called a sparse vector representation. So if you're already familiar with the sparse linear algebra, then it kind of immediately makes sense. But if not, don't worry. So if you think about one hot encoding, in our case, we only have white and red. So, we only need one-dimensional vector. In case of dog, cat, dolphin, we only need two-dimensional vector. But let's say you have thousands of different classes, okay? Then in that case, what you're gonna, the one hot encoding will end up something like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1,000 times, all right? And if you think about it, keep repeating this is kind of a, dumb way to use your memory, especially if you're dealing with big data, right? So you got to be, using something more efficient than this. So the idea of sparse vector representation is to only store non-zero values. Okay. We're going to use only non-zero values. We're going to store only non-zero values as opposed to storing all the zeros. So the idea of this is, actually, I should have created a text cell. So the idea of this is that instead of putting all the zeros like this, let's just, first of all, specify the dimension of the vector. Okay. So let's say that one has 1,000 dimension. Okay. So that's the dimensionality of the vector. Now we're going to specify the locations of non-zero values. So for example, in this case, let's say 13. And then at the end, for those each of those non-zero values, we're going to specify the actual value allocated at that location. So what this representation means is, okay, I have a 1,000-dimensional vector, most of it filled with 0, 0, 0, 0, 0, 0, okay? And then the 13th element, so 0, 1, 2, 3, and blah, blah, blah. Let's, I'm just guessing. This is probably where the 13th element exists. And the 13th element is going to have a non-zero value of 1.0, okay? Of course, there can be more than one non-zero values, right? So position, let's say 3 has a non-zero value of 0.65, right? So in that case, 0, 1, 2, 3, that's the position. And then the value for that position is 0.65. So that's going to be the shape of the sparse vector converted into a dense vector. Okay, I hope that makes sense. So with that being said, let's go back to this representation. Here we have a sparse vector representation. The first thing is the dimension. So we have a one-dimensional vector, which is what we expected, right? And then the first element is where we store the positions of non-zero values. So third position and 13th position in this particular example. In our table, we have an empty list, right? So that means there's no non-zero element. There's no non-zero element, which means it's a one-dimensional vector that is filled with zeros, AKA this one, okay? So Spark, for some reason, has kind of flipped the, the index. So it actually became, 1 and 0, right? So for red wine, the one-hot encoding became 0. And if you actually try to display where the type is white, then as you can see over here, we have some different sparse vector. And what he says is, this is a one-dimensional vector. And at the zeroth position, we have a non-zero value of 1.0. So that's exactly this. Okay. So if that makes sense, we're going to move to the next problem. And as always, I'm keeping my eye on the chat box. So whenever you have a question, don't hesitate to just drop that in. I'll try to answer them whenever I grab a chance. Okay. So what we've just seen is two methods, right? One is called a string indexer, and then the other one that says one hot encoder estimator. And then as a result of that, we have converted our data frame. We further processed our data frame to have a column called type one hot. Okay. So the later process is pretty much the same as what we saw last time. So we're going to now train a linear regression model to predict the quality of wine in this particular example. So we're not going to do the classification, actually. We're going to we're going to predict the quality of a wine by taking in these variables into account, as well as the one hot encoded wine type. Okay, so my hypothesis here is the wine type, white versus red, might have some effect in the prediction of quality. There might be some correlation with quality. I don't know if it is true or not, but that's my hypothesis. So we're going to test that by fitting a linear regression model. Okay. So to do that, last time what we've done was this thing called the vector assembler. So we have to first of all assemble a feature vector, right? So that's going to be our regressor in our linear regression model. So again, from PySpark.ml.feature, that's always the go-to place where you have to convert columns into something else, right? Import vector assembler. Okay, and then we saw the how to use vector assembler. So I'm gonna just quickly type everything in. So again, input columns is what you need to specify, and I'm gonna do that later. And as a result of that, there's gonna be a new column created, and I'm gonna name that as features, and that is my transformer. So assembler is defined as a transformer like this. And assembler dot transform df encoded dot select. Well, let's just stop here, and that's the vectorized data frame. Okay. Now for input columns, I'm gonna need all the way up to this alcohol column, so which is -1, -2, -3, -4. So df encoded dot columns all the way to -4, and then I'm going to need actually the type 1 hot column. So that's another column that I want to include as a regressor, right? So that's going to be my vectorized data frame. So in this vectorized data frame, we have at the end this features column. And obviously, I don't need all of them because I'm not going to use all of those columns. I'm going to use the features column and the quality column. So I could have just selected, only the features column and the quality column. So in that way, my data frame looks more succinct. Okay. So the later part is exactly the same from this point. First of all, you have to split the data set into 70% training set and the 30% test set. So df train is, and the df test is going to define as randomly splitted rows from this vectorized data frame. And then my linear regression model is going to be, well, I think I did not import, from PySpark.ml.regression, import linear regression, right? And my linear regression model is going to be linear regression, and the features column is going to be features, and then the response variable, the label column, is going to be quality, right? So we're taking in these features and then predicting the quality. And that's my linear regression model. And linear regression model is obviously, is it estimator or a transformer? It's an estimator, because the very definition of estimator is an abstraction of the concept of training machine learning model. So machine learning model, in other words, has to be an estimator. So you can fit the estimator to the trained data set, and that will produce a transformer, which is a model. Okay, so LR underscore model is a model that's trained on the DF underscore trained data set. And therefore, LR model can evaluate the test data set and then predict the values for that test data set. So that was kind of, an example, a very nice exercise indeed of, beginning from, reading 2 or more data sets, combine them to create a unified data frame, and then, use estimators and transformers to convert columns into eventually the format that you want to feed into your machine learning algorithm, which in our case was a one-hot encoding, right? And then, using the vector assembler, you could create a feature vector, and then using the feature vector, finally, you could train a linear regression model. So, you know, as a matter of fact, there are actually many other machine learning libraries in PySpark.ml.regression. So if you, you know, trigger the pop-up menu, you can see that there's a decision tree regressor, generalized linear regression regressors. You know, there are so many. And then I think I provided last time a link to the PySpark documentation where you can see the exhaustive list of you know, model that's available in the PySpark ML regression library. Okay, but nonetheless, whichever model you use, the usage is going to be, you know, almost the same, almost, you know, almost exactly the same. So as far as you understand the concept of estimators and transformers, you should be very fine. Okay, so we're going to move to our next topic. Now, one thing that you may have already realized is, well, first of all, this is kind of, although the notion of estimator and transformer makes everything kind of nice and clear, but in the meantime, it's kind of annoying to, you know, fit a data frame and then create a transformer and then transform, you know, a data frame into another data frame, and that data frame goes into vector assembler and blah, blah, blah. This is kind of, you know, annoying in some sense. From the readability of the code perspective, the code will become messier, you know, as it is kind of hard to, you know, see what goes into the model and what comes out of the model, and how that feed into, you know, the other model, other estimator and transformers, and so on and so forth. So, you know, managing that becomes a little bit, you know, overwhelming, especially if you have lots of estimators and transformers. Okay, I mean, in the real world problem, I mean, we're using this wine quality data set, which is actually quite a nice data set, which, you know, all the data rows and everything has, you know, nicely kind of, you know, cleaned up, right? But you know, if you guys already started the consulting project, right, the book company project that I assigned you to as a homework, you probably have already realized that it's actually quite difficult to clean up all the empty rows and, you know, messy columns and, you know, things like that. So it is actually quite common in real world where you have very ugly data sets. So that means you're going to need to transform, you know, your data frame, you know, through multiple stages in order to produce a clean data set. So in real world situation, you're going to use, you know, not only just a vector assembler, one hot encoder, and, you know, those kind of thing, but you're going to, you know, need to define a lot of different transformers and estimators. And that's when the life becomes, you know, quite complicated, because you have so many data frames kind of, you know, toast back and forth between transformers and estimators, and, you know, everything gets really crazy. Luckily, in Apache Spark, there's this notion of pipeline, okay? And pipeline is the very concept of, you know, computational graphs. So which information goes in as an input to which computational module, which in this case is either estimator or transformer, and how does that output, you know, where does that output goes, you know, to which estimator or to which transformer it goes. I mean, all of this is defined in a computational graph. And Apache Spark has this object called a pipeline, where you can explicitly define the information flow, okay, as a sequence of, I mean, not necessarily just one-dimensional sequence, but as a graph of transformers and estimators. So here's what I meant by that. So if you think about it, we had three steps. We had one called a string indexer. So I'm going to just copy and paste the code from the above. So that was the first thing that we've done. And for the sake of simplicity, I'm going to just name that as indexer. And the next step was the one hot encoder. And that was, again, I become lazy. So I'm going to just copy this one hot encoder estimator. And that was the second set of estimator and transformers. And then finally, we used the assembler, right? So that was the third step. So these three were essentially the steps that we conducted before putting our data into machine learning models. So before string indexer, at the very, very beginning, we have a data frame, right? we had this data frame df, which was the union of the red wine data set and the white wine data set. And then at the end of assembler, we produced, df vectorized, right? So in the middle of that process, there's so many lines of code that converts one data frame to another, creating a transformer and so on and so forth. But essentially, these are the 3 steps that we have undertaken. So in the concept of pipeline, and this can be actually very useful. Using the concept of pipeline, what you can do is simply define the flow, the individual steps, okay, of estimators and transformers, and then just define stages as a list of those estimators and transformers. So these are 3 stages of our process. And what I'm going to do is to create a pipeline. And to do that, I actually need to import pyspark.ml import pipeline. So I'm going to create a pipeline, that's a small p, with this pipeline object where the stages are defined by the array that we just specified over here, okay? So that's my pipeline object. And pipeline object is another estimator, because pipeline is a collection of estimators and transformers. So what you're going to do is then to pipeline.fit to first of all take a look into the data frame. And that's the original data frame that we put in. And that is going to create a pipeline model or pipeline transformer, okay, which is ready to transform this original data frame df into the vectorized version. So the final output, skipping all the intermediate processes. So df underscore vect is going to be pipeline transformer dot transform. And as an input, we take in a data frame df, and then the output is the vectorized version. And, needless to prove, the vectorized data frame is going to look exactly the same as before. So see, we have about 7 lines of code, except for, from import something. We have 7 lines of code, which kind of simplifies how many lines over here. We have 2 lines for vector assembler. We have 3 lines for Hot Encoder Estimator, and then we have another 3 lines for string indexer. And we ended up defining like index transformer, df indexed, encoder transformer, df encoded. So there's so many intermediate outputs, right, and intermediate throughputs in between the process. Here everything is nice and clean. So we have only the initial input, which is df. Actually, I should have done this to be rigorous. Sorry, I just copied and pasted, which doesn't make any difference, but to be rigorous. So instead of creating those all those intermediate throughputs, now the code becomes much cleaner. But on top of that advantage, additional advantage is that if you create a pipeline, then internally Apache Spark kind of further optimize the collection of transformers and estimators. So each individual transformers and estimators are somehow optimized, but if you call them line by line, one by one, then from the global perspective, if you look at the overall process, they're not terribly optimized. So by creating a pipeline, additional benefit in addition to the readability of your code, is that you're making the pipeline even further optimized, so that all of the transformers and estimators are somehow kind of get merged and then becomes optimized, so that instead of running everything as a sequence step by step, running a pipeline at once is going to be computationally more efficient. So that's another benefit of creating an Apache Spark pipeline. Okay. So in this lecture, we have seen many different things. In fact, I think, like I said, this supervised learning lecture is, this lab is probably one of the most important lab section throughout the semester, because we covered quite a bit of different things. At the beginning, we talk about the very notion of distributed optimization algorithm. And then, we move on to the Spark. And Spark internally uses a distributed optimization algorithm to handle large data sets. And then the way that Spark implements all that is based on the notion of estimators and transformers. So it's similar to, mappers and reducers in Hadoop ecosystem, right? Hadoop uses mappers and reducers. Spark uses estimators and transformers. And, although there's only, slight difference conceptually, the way that the estimators and transformers are optimized gives a tremendous benefit compared to previous Hadoop MapReduce. So according to what Apache says in their website, logistic regression, for example, implemented in estimators and transformers compared to mappers and reducers, it's about 100 times faster. Of course, I think that's something you can just believe without a suspicion, but Spark is indeed much faster than MapReduce in many cases. So, and that comes from this very notion of transformers and estimators. So it's important to understand the concept of estimators and transformers, right? And then, finally, we just covered the concept of pipelines, which is basically, how we lay out those estimators and transformers, and, how we connect them, right, in the process could be defined in the pipeline. And by having a pipeline, you can even, you can accelerate it even more, so that all the data processing pipeline could be, defined in an optimized pipeline transformer object. Okay. So that's it for the first half. And the second half is going to be continued in the next video. Thank you very much.